Hi everyone, welcome to Discussion 10 walkthrough video covering shortest paths and MSTs. To get started, some announcements that are relevant by the time this video is released on Wednesday. Midterm 2 requests are due on Wednesday, March 31st. The Build Your Own World partnership form is also due Wednesday, March 31st. The full grader logs for Gitlet will be available starting Thursday, April 4th, that's a typo. And Project 2 is also due on Friday, April 2nd. And that is it for announcements. We're going to get started doing some content review. So Dijkstra's algorithm is an important algorithm that we're going to cover in this class. We previously learned that breadth first search can help us find paths from the start to other nodes with the minimum number of edges. And so in this example, the shortest path from A to E, just based off the number of edges, would be taking this and then this. But that's just the number of edges, and not all edges are created equal. Some of them might be harder to traverse than others, or in other words, have a greater weight or maybe distance, if you want to call it that. And so if we want to take into account the edge weight, then we need to use some sort of different system because BFS and DFS don't account for the edge weight, only just the number of edges. And so this leads us to Dijkstra's algorithm. And Dijkstra's is a method of finding the shortest path from one node to every other node in the graph based off the edge weights. And so now when we say shortest path, we're not talking about this path, which only has 2 edges, but a total weight of 7 plus 2 is 9. Rather, the shortest path based off edge weight is going to be this one that has a total cost of 1 plus 2 plus 1 plus 1 plus 2. And I can't do math off the top of my head, but I believe that's 7. And so this is a shorter path based off edge weight. And that's the path Dijkstra's algorithm would find specifically starting at A going to E. And so that is what Dijkstra's does. And the way we do this is by using a priority queue that sorts vertices based off their distance to the root node. And so the idea is if our priority queue prioritizes visiting short paths first, then we're going to see those before we bother going down a long path, right? And so when our priority queue gives more value or says we should go down shorter paths, once we, for example, pop off a node off the queue, we know that that was the shortest path there. The proof for this is covered more thoroughly in lecture, but that's just a recap on why we use the priority queue, because we want to prioritize taking shorter paths. And so for B, in this example, we would want to take this path to get there. And we're going to notice in the priority queue, traversing the edge to go directly to B right here would always have a priority of 7. And so it's not very highly prioritized because right now that's pretty expensive. But we would have these edges that have higher priority to traverse, or in other words, these nodes are in the queue with higher priority because they're closer to A as far as we know. And it ends up working out for us because we were right. There was a shorter path to B. All we had to do was hold out and continually look at closer nodes before we look at something that's far away, because who knows, maybe there is a shorter path to that currently far away node. And so that is the essence of Dijkstra's algorithm. I will briefly go over the steps, but you're probably going to find it more helpful when we go over an example together with a real problem. The steps for Dijkstra's algorithm involve popping a node from the top of the queue. And so we'll consider this our current node. So for example, maybe we're just popping A and we're starting here. So we just got started and we popped A. Then we are going to add or update the distances of all the children of the current node in the priority queue. So to begin with, before we've seen anything and we're getting started at A, we can't know anything about the distances, right? We haven't seen it, we haven't looked at it. And so we just go, okay, I don't know how far away every other node is. I'm going to assume it's pretty far. But once we pop A off the queue and we're looking at the current node, we can take a look around its children and say, okay, actually, B is 7 away right now and C is 1 away from the start right now. That's what we know, and that's our best distance. So at every step, you are going to take the current node and look at your children and see, have I found a new best distance or a best way to get there? And so you add all those children and their best known distances to the priority queue. And of course, we have to make sure our priority queue is staying sorted So technically our priority queue, if it's done correctly, when you add things, we'll automatically put them in the correct order. But when we're doing it on paper, we always just want to make sure that our priority queue is sorted. And then we can finalize the distance to the current node from the root. And so what this is saying is once we pop something off the queue, we have guaranteed we found the shortest path to it. And again, that's a proof that will be covered more in lecture. But the idea is that once you pop something off the queue, that means it must have been the next closest thing to the root from the queue. So you know that any other node on the queue is not going to have a shorter path to the current node because the current node was the closest thing to the root on the queue. In other words, all other nodes have greater distances from the start than me. So how could I go through another node and get to the current node in less edges, right? Assuming all edges are positive. And so this is why we finalize the distance once we pop it off the queue. And then we just go back up and repeat this all, looking at the next thing on the queue. And that is Dijkstra's algorithm. I like to think of Dijkstra as a traveler without a map who arrives at one city and just reads a street sign to see how can I get to the other cities and how far away are those cities from here? And I don't know if you've ever seen one of these signs, but maybe you can imagine if we pull up in, I don't know, Los Angeles, and you say, oh, look at Miami is somehow 211 miles away. And you see Detroit is 1,233 miles away. And so on this little poll, the closest thing is Miami, so we might go there next. But we're not going to say for sure Detroit is, 1,233 miles away. Because maybe if we go through Miami, there's a path that's only 5 miles, and then we could get to Detroit in 1,238, right? And so that's just a hypothetical, but the idea is that we're just going to go to the closest place, but not go anywhere else as long as there's a potential that there's a better path. And you just get to see this once you arrive at a city. So you don't have a map where you can see the bird's eye view as the traveler or from the point of view from the computer. You only get to see these edge weights once you've arrived at a node. You don't have the bird's eye view that we have. You have to manually traverse your way through it. And so that's why I say a traveler without a map. The traveler doesn't accept the distance as final until it's clear there's no potential shorter routes. Similarly to how we only finalize a node once we pop it off the queue, which means it had the next shortest distance. That is Dijkstra's algorithm. We will go over an example that will hopefully make all of this a little more concrete. But before we do that, we want to talk about A-star search. And so A-star search is very similar to Dijkstra's, except I would say the main differences are that unlike Dijkstra's, which finds the shortest path from a start to every other node in the graph, if you want it to, A-star can only be run from the start to a goal. But the benefit of this is that when we have a specific goal in mind, we can now maybe talk about the idea of a heuristic. And so a heuristic is an estimate of a current vertex's distance from the goal. And so the estimate says, okay, for example, if I am at B, I'm going to guess that I am one distance away from E, the goal, which is highlighted in yellow. And note that the heuristic doesn't have to be perfect. If it was perfect, then we would know everything and we wouldn't have to run A-star to begin with. But the heuristic is sort of our estimate that says, okay, I don't know for sure how far this node is from the goal, but I'm going to guess it's around this, and we'll hope our heuristic is accurate enough, right? And so the heuristic is our guess for how far we are. And so interestingly, like Dijkstra's, where our priority was the total cumulative distance from the start, in A-star, our priority in the queue is now going to be the sum of the total distance from the goal to the current node, as well as our estimated distance from the current node to the goal, in this example, A and E, right? And so when you sum all this up together, it gives the total estimated distance from the start to the goal, right? And so this is really great because now what we're basically doing is we're putting things into the priority queue and visiting things first that have the estimated total shortest distance from the start to the end. And so unlike Dijkstra's, where we were just sort of greedily saying, okay, I'm just going to try to stay close to home, the heuristic sort of lets us peer into the future. It's an estimate because we don't know the future for sure, but it gives us a clue on, hey, I think this is a better direction to go in ultimately because we're heading in the right direction now. And so that is A-star search. And very similarly to Dijkstra's, you're just going to pop a node from the top of the queue, your priority queue. Then you're going to update all the children and the distance. And so I should say, not the distance, the priority will be the sum of the distance up to that child node and our guess of how far away the goal node is, our heuristic. We're going to make sure our priority queue is sorted. Again, when you add to a priority queue, this should already be happening implicitly, but we just want to make sure if we're running the algorithm on paper that it is. Then we're going to check if we've hit the goal node, and if so, we stop. And we'll repeat this while the priority queue is not empty. And so that's A-star. A-star is very similar to Dijkstra's. We just have a specific goal in mind, and we have a heuristic that lets us know if we're heading in the right direction or if the next node is estimated to be close to our goal. Finally, pivoting away from shortest paths algorithms, we're going to briefly talk about minimum spanning trees. A minimum spanning tree is a set of edges that connect all the nodes in a graph while being of the smallest possible weight. And we can sort of break down this definition, minimum spanning tree. So a tree, as we've discussed, is fully connected, which means every node is included. We don't have any like islands floating around, right? That aren't connected to anything. And there are no cycles. So that's the tree part. And spanning, I think, sort of covers this fully connectedness of the tree, right? That every node in our graph is included in our tree. And the minimum is the interesting part. It means that the total edge weights, the sum of all the weights in our tree, is the minimum possible for any given tree we could form from this graph. And so in this example, we have this graph, but the only edges we're including in our minimum spanning tree are the ones highlighted in blue. And so you're going to notice, technically, we could have had another spanning tree that included this edge, but did not include this one, right? And this would be a tree because there's no cycles and every node or vertex is included, but it's not of the minimum weight because including this edge with weight 7 in order to get B there or like have B attached to our tree is much more expensive than including this edge with weight 1. And so whereas our original minimum spanning tree had a total weight of 1 plus 1 plus 2 plus 1 plus 2 plus 1, or sorry, not 2. Just the edge weights that are included, which are in blue, and that would have had a total weight of 7. If we had included this edge and not this one, we would have had a total weight of 7 plus 1 plus 2 plus 1 plus 1, 7, 1, 2, 1, 1, which brings us to 12. And so that is not the minimum spanning tree because the sum of its edges is not the minimum total that we could find. There was a lesser weight tree, which was this one, where we include 1 and not 7. So we're looking basically for the lightest tree we can form that connects all the edges in our graph. This tree might not be unique if there are multiple edges of the same weight. So for example, if our graph looks like this, and we want to know what's the minimum spanning tree, technically this is a minimum spanning tree because it includes all the edges or includes all the nodes and there are no cycles. But this is also a valid minimum spanning tree, right? And so you can see that there are multiple ways to form a valid minimum spanning tree when you have multiple edges of the same weight. Of course, that's not always the case because, for example, if your graph looks like this, you have a duplicate or duplicate edge weights, but there's still only one minimum spanning tree, and it's just this whole graph, right? So I want to emphasize that if there are multiple edges of the same weight, it may or may not be unique. However, if all the edges are of distinct weights, then it must be unique. The proof for that, I think, is covered more in CS170, but it's definitely interesting if you want to go research that on your own. There are two main algorithms for finding MSTs in this class, prims and crucibles. Both of them are different but totally valid, and we'll go over them in more depth when we go through the worksheet. And that is the content review.